I consider dissemination very important because that is how transmission works for teachers, for the person, for the general public. I have 525 conferences, 300 videos, 16 books and 22 years of writing the Pleasures of Thought section in the Bulletin of the Mexican Physical Society. The different careers have training courses. Disclosure is valuable, but it is even better if it updates the population with questions that require reasoning. Here we have a photograph downloaded from the internet that says 1 photo a day for 28 days. The place is clearly a photo montage. I hope you know why. I like the question of bringing an electric charge closer to a trickle better. Here we see Hewitt's answer. Consider that water is attracted to it because it is a molecule that has a permanent electric dipole. So, if there is a negative charge coming towards it, then the molecules rotate and it is the hydrogens that come towards it. The more charges, the closer there is an attractive force. In case the charge is positive, then what brings you closer are the oxygens. However, there is a force of attraction. It's a plausible, elegant answer, but it's wrong because Hewitt forgot that water is conductive when a charge approaches it. The charges free to move inside the conductor go to the surface until they manage to cancel the internal field. That is, the field induced by the surface charges is such that it zeroes out the macroscopic field inside the conductor and therefore there is no force on the charges inside it. I like this more. A compass to measure magnetic fields. The compass detects horizontal fields. It is with the compasses we can find the field of this point to the north. So if we put the magnet so that its field is horizontal and perpendicular to the field of the compass, we can use the compass to measure it. That is, the angle theta, its tangent to theta will be the field of the magnet divided by the terrestrial field. This is very simple. We have a compass, a ruler, a magnet. We set the compass to the zero of the ruler and move the magnet by different distances. And we are measuring. This angle deviates over here. And that will tell us the magnitude of the magnetic. We can measure the terrestrial magnetic field with a smartphone that has programs to measure total magnetic fields. So it has X component, Y component, Z component. So the magnetic field needs horizontal component. If we make this field here 0, then the component and the levels are on this horizontal completely. But if we locate the position of the sensor in 3 magnetic sensors, then we can move the magnet along a line perpendicular to the x-axis and get the internal distances and field measurements and directly get the magnitude of the horizontal magnetic field. A very nice experiment is to have small magnets like the previous ones, glued. To cork so that they float and put a plate with water in which the magnets float surrounded by 36 magnets, but of the same polarity. The magnet floating in such a way that everyone repels it and a magnet goes alone to the center. But if there are 2 of them, and they get closer, but they repel each other. So if there are 3, they form a triangle. If there are 4, an experiment that serves for life. We are driving a car and suddenly a truck stops on a street and we were going 50 kilometers per hour. That is, 15 meters per second. The friction is 0. What do? Brake hard? Or we use the force of friction to rotate and then we would arrive at a curved line. It is an arc of a circle. But let's see what physics tells us about the distance to brake in these conditions is calculated with constant acceleration and the radius of gyration is at constant speed. That is, the turning radius is always twice the distance to stop. Then the red line that marks the radius of gyration. And we see that we can also deviate as 2.8 meters. It is the maximum that we can divert the car. But if we use the force of friction to steer the car, we don't change the magnitude of the velocity because it is a force of 90 degrees. So we're going to crash at 15 meters. On the other hand, if we brake first, absolutely nothing happens. We do not reach the workshop and everyone is saved. What does this mean? That in this case we do not have time to think. Let's stop first and then live. A classic experiment is the Millikan experiment for the quantization of electric charge. The forces in the fall of the drop are the friction with the air is equal to its weight, that is the force of friction with the air of a droplet falling freely. So that it goes up for that we have to put in an electric field E. Produces a force on the charge as QE. The net force is minus the weight of minus mg and will be equal to the force of friction, but now up. Yeah, here we clear that he. In the equation above. Using the equation below, we were able to show that Q is equal to 6 pa between B of longest fall of rise. That is, by measuring the rise drop we can measure the charge in the drop. Here is the original data Millikan used to receive the Nobel Prize. And we notice that the decay time is pretty constant. 11 point. What does this mean? that the air convection speeds are negligible compared to the speeds of fall due to gravity, and so these data are reliable. In fact, he also measured the time in half to confirm that there was no convection, and from here to here are data that we are not going to use because it is Millikan's interpretation of the matter. In other words, the load is simply proportional to the sum of speeds. Here is Millikan's interpretation of the data calculating the force, the charge Q. So we find and ordering the charges that are equal. We find that there are 3 with 1 electron charge, 4 with 2 electron charges, 5 with 5 and 6 electron charges, and 1 with electron charges. This was the tiniest drop you could find, Millikan. His normal data is stronger, heavier, and then you have to make the analysis more complex. So, data from others from another Millikan post. And we see that 16, 17, 18, 20, 21, 22, that is to say, the school laboratory is already trying to do this experience, with very little thermal inertia and the convection is very high. And then they do not find repeatability in the rate of fall. Experiments are useless if the rate of fall is not repetitive. Unfortunately, teachers have not realized this and continue to use it. Another magnet that can be practically used with children. Another experiment that can be done practically with children of any age. It is asking them to draw the field of a magnet within the Earth's magnetic field. And starting here, at the edges, we put the compass and we move towards where the compass indicates. And we draw a line of force. And another, and another, and another. But if the magnet is oriented so that it repels the Earth's magnetic field, this is a kind of bag in which all this does not fit. But if we invert it 180 degrees so the magnet now attracts the lines of force of the Earth's magnetic field, sucks them in on this side and spits them out on the other side. If there is still a region in which the magnet is the one that controls the lines of force. But as an experiment, and you can do pretty much any data, it's interesting. Hello. Other, the problem that I exposed of 2 equal charges of different signs separated by 10 centimeters, solved with Excel. If the positive charge is double the negative charge, all the lines of force can be calculated. We note that half of the lines of force that comes out of the large charge serve to cover the small charge and the rest go to infinity and are going to be seen as a point charge. But the drawing is very nice and it is satisfying to think that we can see it doing the same but with the magnetic field. We have to use the expression for the point dipole field. The field of M at point R is then this equation. From there we can divide it into a component in polar coordinates and the 2 components have x and y components, and see the magnetic field. But then we can solve for the sum of the fields and this is the result. When the magnet attracts the Earth's field, there is a graph very similar, well, similar to the one drawn for the magnetic field that repels it. I hope to end by emphasizing that learning is more than just teaching. And this cartoon shows it very clearly. He teaches as if he had stripes. I can't hear him whistling. I said that I taught him, not that he learned.